So good evening. Is it full screen? Yes, sir. Okay. So let's start. So good evening to all of you. Myself Samresh Ghosh from IIT Roorkee. So the title of this NPTEL course is Characterization of Polymers, Elastomers and Composites. This is week 10, and this week we'll discuss about microscopy, both optical and electrical microscopy. So already the module has been taught by Professor Santanu Chattopadhyay, and here myself Samresh Ghosh as a TA. To clear your doubts and we'll discuss. So, what is microscopy? We'll discuss later the difference between spectroscopy and microscopy. But for this time being, the microscopy actually, of course, it is uh, analysis the morphology or structure in micro or below micro level. So, microscope are devices that are used to magnify small objects, and they come in a wide range of shapes and size and use many types of illumination source, for example light, electrons, ions, x-ray, etc., and even sometimes mechanical probes are used to illuminate the objects. And after that we should collect the signals to produce an image. Now microscopy is the technical field of using microscope to view samples and objects that cannot be seen with our naked eye. So obviously we have the limit through our eyes. We cannot go maybe a few points millimeter. If we want to see the objects, those have very small size, for example any biological species, we need microscopy. And microscopists explore the relationship between structure and properties for a very wide uh, variety of materials. It may be polymers, it may be composites or biomedical sample, and sometimes also very hard type of metals. Now, what are the specific terms? Before going to the details, we need to consider the source of the light or illumination, the contrast and resolution. These two are the very important term. We will discuss in the next slide. Then magnification, numerical aperture, and bright and dark field image. Now from this image you can say that with our eyes maximum we can see up to 100 micrometer. Below that we need microscope. So there are different microscope, for example light microscope where visible light is used, and then the most advanced one are the electron microscope. And through electron microscope we can magnify few lakhs, and we can visualize even the structure of a DNA or any virus or any bacteria species, and also we can go up to crystal size through the electron microscope. Now the term that I have already used, the magnification. What is the magnification? Magnification means that how much large an image can be processed as compared to its the real size or real life. So this is the ratio of the size of the image divided by size of the object. So that is the magnification. And next important term is the resolution. So the resolution means that an object, how the smallest distance between two objects we can see as a discrete object. So this is the amount of information that can be seen in the image, and the smallest distance below which two discrete objects will be seen as one. For example, if you see this image, so it is showing like a single uh, hump. But if we magnify it, if it has the very high resolution, we have some uh, mechanical instrument so that we can resolute this, and we'll see this is not a single object. Basically, it is consist of two different objects. So any object that is less than the half of the wavelength of the microscope illumination source is not visible under that microscope. So this is very important. For example, if you are illuminating or you are trying to object any species or any objective with a wavelength 400 nanometer light. So if the dimension of that object is below 200, we cannot see through the 400 nanometer illumination light. So it must, the wavelength of the light, that is the limiting limitation of any illumination source. So if it is visible light and an object has the dimension below 200 nanometer, we cannot see it. The next important term is the contrast. So what does it mean? So contrast is the contradiction, or it is the, basically in a general say, you can say it is the fraction of intensity. So it is the luminescence or color that makes an object or its representation in an object or display distinguishable. If we see these two images, both have the almost same resolution, but these black marks are more prominent here. So that is because of the different contrast. In visual perception of the real world, contrast is determined by the difference in the color and brightness of the object and other objects within the same field of resolution or same field of view. Now, what is the phase contrast? Phase contrast is the technique in microscopy of introducing a phase difference. So, for example, if you have a composite type of material, for example, let's assume this is a rubber matrix and these are the fillers. Now, if I want to see what is the exact dimension, from this you see the periphery of this circle is not that much clear, but here you can exactly measure the diameter of the spherical. So it is the technique that used in microscopy to create the phase difference between the parts of the light supplied by the condenser so as to enhance the outline of the sample or the boundaries between the parts that are differing in the optical density. So of course these two, if it is a two component system, so they have their different optical density, and based on this technique we can very clearly visualize the dimension or the boundaries. Sorry. Now, what are the different modes of light interact with any matter? So we know because of its electromagnetic radiation, light is electromagnetic radiation, and also it has particle nature as well as wave nature, and these two nature have their own different properties. If it is a rays, so obviously there is reflection and refraction. So the incident ray is coming and it is reflected back. Waves, so waves have different physical phenomena like interference. We have already discussed what is interference, diffraction, and polarization. And if it has a particle nature, so because of the having particle nature, it will show some different property like absorbing, scattering, or fluorescence. So here the refraction, what does it mean? Refraction means in two different medium, it has a two different refractive index. For example, if it is a pencil is dipped inside a water and you visualize it from the air medium, so you will see like the pencil, the exact location you cannot see. Actually, it is uh, making you a fool. So the exact location is here, but if I observe this object from air inside the water medium, I will see the object is here. That is because of the different diffractive index of uh, the visible light in air and water. And if the interference is occurring because of the wave nature of the light, so we know if they are in the same phase, it will make a constructive interference. If they are in the opposite phase, it will make a destructive interference. So based on these different properties, there are different technique to analyze through the microscopy. And we also discuss what is diffraction during the XRD. So it is a first reflection followed by interference, and it will create this dark and bright uh, image. And of course, because of the polarization, through the polarization, we can polarize the electromagnetic radiation. So since light is also electromagnetic radiation, we can polarize it, and by polarizer, we can determine different properties of any material through the polarization of the light. Now, first we will discuss the basic before going to the details in optical microscopy. So we have already known that how a image can form through a plane mirror. So this is the object from a sunlight, the incident light is coming and then reflecting back, and then if you make a plane mirror here, you will get image in the opposite direction. There is also in optical microscope we needed lens. So basically there are two different type of lens, convex and concave, and we also know, or we have already read during our class 2 level, the convex and concave, the parallel light after passing through this lens, it will merge here, and their distance is called the focal length. And if it is a concave, so it will be splitted away from each other, and that is because it is the arrangement of prism in different direction. So what is the focal length? The focal length of an optical system is the measure how strongly the system converge in case of convex or diverge in case of concave lens. It is the inverse of the system optical power, and a positive focal length indicates that a system converges light, while a negative focal length indicates that it is the system diverges the light. The next term is the numerical aperture. So numerical aperture of a microscope objective is a measure of its ability to gather light and resolve the fine specimen. So higher will be the numerical aperture, higher will be the resolution of your microscope. The image forming light waves pass through the specimen and enter the objective in an inverted cone, as this is the inverted cone, and the longitudinal slice of this cone of light shows the angular aperture, a value that is determined by the focal length of the objective. So this is the equation, numerical aperture equal to n into sine mu. Mu is the angular aperture, and the lower will be this number, higher will be the numerical aperture. The angle mu is 1/2 of the angular aperture and is related to the numerical aperture through this following equation. N is the refractive index of any medium where the image is forming. So here it is written that N is the refractive index of the imaging medium between the front lens of the objective and the specimen cover glass, and the value can be ranges from 1 since it is in air. If it is in a special oil, immersion oil, if it is immersed in a oil, then the value of the N will be the 1.51. From the equation, it is obvious that when the imaging medium is air with a refractive index n equal to 1, then the numerical aperture is dependent only upon the angle mu, whose value, maximum value is of course 90 degree. So how the incident light is focusing on the object, in which angle it is the incident is happening. If it is in the air, only the angle of incident is the uh, basic parameter through which we can tune the numerical aperture. Now what is uh, bright field and dark field images? So it is showing that this one is the bright field image and this one is the dark field. So first of all, why we should do that bright field and dark field? Because to create the contrast, much more intense contrast you can say. So the most common source of image contrast are particle mass and crystallinity, because depending on that mass and crystallinity, the scattering will be different. Heavier atom scatter electrons more intensely than the lighter atom, and hence the bright field mode, the regions with heavier atom are darker, while the dark field mode, these regions are brighter. So since we have already discussed during XRD also, the heavier atom can scatter electron more intensely. For example, that's why if it is a only polymeric system, it is little bit the flux of electron generation will be less, and that's why we should go for this bright field image taking or dark field image taking. Now the bright field area that serves as the background for object viewed in an ultra microscope. So it's, you see, if I want to measure the dimension of this fiber or rod, so it is much more clearly visible in case of dark field image. That's based on this, that whether there is a heavy element present or not, we will go for the bright field or dark field. Now what is the difference between spectroscopy and microscopy? So this is the image of a, so obviously here the scale should be mentioned. Until and unless there is no scale, it has no uh, uh, it is not accurately actually represented the data. If it is, for example, it is a 10 millimeter, so we can say what is the dimension of this particle. Until and unless there is no scale, I cannot say what is the dimension. So while microscopy is used to visualize object, spectroscopy is used to determine the spectral lines or energy of a sample. Now in both cases, we use the electromagnetic radiation. In case of spectroscopy, we also use electromagnetic radiation, and in case of microscopy, we also use the electromagnetic radiation. Now what is the difference? Now in case of, for example, here it is showing the absorbance, and we are plotting the absorption versus wavelength. From here we are getting the chemical structure of the molecule. But if I want to observe what is the morphology, or what is the physical uh, uh, visualize, I have to, if I have to visualize that what is the surface morphology or what is the dimension of a particle or other physical parameters, I should go for the microscopy, because here is also after uh, the interaction with the electromagnetic radiation, we will collect the signal and we will process those signal to create an image. That is the basic difference between the spectroscopy and microscopy. After getting the signal, in case of microscopy, we are arraying those signals to make an image. But in case of spectroscopy, we do, we are getting the signal, and we are not making an array or something like that. So now start what is the optical microscopy. This is the very first form of microscopy. So around in the 1630 or 1640, in that era it was developed, and also it is referred as a light microscope, because here the visible light is used to uh, visualize any object, and it is the most commonly used system in different uh, areas. And there is also use of lenses, single lens or more than single or two, three lenses, to magnify the images for very small object. And this is the oldest microscope, and optical microscope are the simplest and most used microscope. So these has a basic two phenomena. It is the most simplest one, and we can magnify it just by changing the number of lenses, and also we can create different contrast. And here we use the visible wavelength of light to see the object. So this is the simple mechanical, or it is the technique or principle how we observe through a microscope any objective. So a simple microscope is a magnifying glass that has a double convex lens with a short focal length. Example of this kind of instrument include the hand lens or reading lens. When an object is kept near the lens, then its principal focus with an image is produced, which is erect and bigger than the original size of the object. So you put a lens, this is the object. After from the source of the light, the reflecting light is coming in this direction, and then through the lens it is coming through our eyepiece, and we are visualizing this object here. So this is the larger image compared to the original object size. So how our eye is capturing? So obviously first it is the reflected light, this is coming from this object through this lens, first coming to our cornea. Then before the cornea there are other eyepiece or objective lens, and before that we have different cell to uh, differentiate the color and intensity, and before that there are some uh, neurons to uh, make the image data, to form the image. So that our brain actually doing that first to form the image by after getting the signal from the neuron. But before that it is first generating a through the cornea and eyepiece lens, it is forming an higher size, larger size, but in opposite direction actually it is forming the image. But through our brain we are observing the object at the same direction with a greater size. Now what is compound microscope? So this was the very simple microscope initially. Now in compound microscope we are increasing the number of lenses. So it has a high magnification compared to the simple microscope, and that uses 2 and even above 2 lenses to multiply the level of the magnification. The first lens is referred to as the objective lens. So this is the first objective lens. This is your object, and it has typically a magnification to 100 times. And the second lens is known as the eyepiece lens. So this is the eyepiece lens, and you are here, the observer is here. So first, after reflecting the light from the object through the objective lens, the light has came here, and then again through this objective or eyepiece lens, the light is coming to the observer eye, and then the image is forming in opposite direction with a much larger size. Now next, confocal microscope. So this is the state, one of the state of the art of microscope. So there are two different mode. So confocal microscopy, most frequently it is used confocal laser scanning microscope or CLSM. So this scanning and transmitting, there are two different mode. So obviously in case of transmitting, the light is penetrating through the object. Now in case of scanning, what actually we do, we have a region of interest ROI, and through each point I am making the interaction and I am getting the data from the each point. In that way it is scanned. So what it is the benefit? So if it is in scanning mode, it will give you more intricate structure or feature that can be provided, and obviously for that you need a very pinpointed radiation, so that it can interact each and every point, and after getting the signal from each and every point you will prepare the image. Like for example, if uh, this is my region of interest, so from each point I'm getting in that way. So in that way I'm scanning it from each and every point. So this is basically, it is not a continuous line. There are very small point here, and after interacting with each and every point, I'm getting back the signal, and after that I make it a arrangement through the software and preparing the image. So in that way, confocal microscope will give you more intricate structure of any objective. So here you need a special pinhole. And why I need a pinhole? To make a pinpointed radiation. And capturing multiple two-dimensional image at different depth in a sample enables to reconstruct a three-dimensional structure as an optical section. Yes, yes, yes. Your sample is here. Your sample is here. This is your sample. This is your sample. So what does it mean when it is the depth of sample? That means when it is pinpointed, though there may be, you can get just by changing the angle of the splitter, you can radiation can penetrate a little bit inside your sample. In that way, it is getting the data from the depth. Or otherwise, you can do very cleverly. For example, take data from the surface. After that, to make a slice. So just put the initially surface slice apart and get the second slice data. For example, if you say there are three different slices, so first you take the surface, then remove this slice, get the data from the second one, remove this second one, and get the data from the third one, and through which you can get, or you can construct a three-dimensional structure of your objects. That is the beauty of the confocal microscope. Which one? Yes, yes, yes. So here your source of the radiation is laser. So because why I need? Because I need, since it is a scanning mode, so I need a pinpointed radiation. So that's why I need laser, so that obviously it has at least the width of the radiation, the wavelength variation will be low, and even after to make it more pinpointed, I need a confocal pinholes. So through which the first incident light is coming, and again before detector there is another pinholes, so that after reflecting back, again it is pinpointed. uh, if you don't use laser, if you use some other sources, for example, if it is generating the visible light, so of course there are a very wide range of radiation with different wavelength. So in that case, maybe you need more pinholes, confocal pinholes. In that way, you can also make it a pinpoint. Yes, actually, this is showing that from different layer. So, for example, red is coming from the second, the green is first, and then and the last one is also green. So, this is from the different depth of your material. The reflecting light are from different depth of your material. So, just to make uh, more to identify, so this, that's why it is making green, red, and green. So, first one is the from the initial slice, and if you cut the first slice, then the red is coming from the second slice. That means it is the depth profile. That's why it is making different color. Yes. Yes, actually that's why I need the confocal pinhole, na. I don't want to get the every radiation after reflecting. I don't want every scattering light. I need a very single, or I mean the narrow radiation, narrow wavelength radiation. That's why I am making that pinhole. So because if your material has different elements, and obviously based on the material, their the scattering will be different. Okay, and here you see that's why there is only single red. This is single red, and after reflecting back, so of course because of different optical density of your material, the the reflected light be in different angle because of the optical density is different. But I need a very specific one. That's why again I put another pinhole here, so that my contrast will be much higher. Otherwise, if it has a very high scattering, you will get a very poor contrast. So your image will be little bit hazy. So to make the image very high contrast, I need a less number of scattered radiation. So that's why I make here another pinhole. And why the scattering will be higher? Because of course the optical density, if any composite or material or heavy element is present, the scattering will be high. Is it clear now that why I need another pinhole here? Just to reduce the scattering that is happening after the reflection, after incident light, the scattering will be higher if there is presence of heavy element or different phase. To reduce that, because I need a high contrast image, for that I need less scattered reflected light, less scattered reflected light. That detector, that is a simple camera. That is simple camera. Actually, that you need to do either just manually, what I have already told you, that through software you may also do, or otherwise, for example, if you have a 10 millimeter thick sample, so first take the data from the surface, after that 1 millimeter cut and get the data from the below surface. In that way, you can after getting the all the data, then you need a software to make a three-dimensional structure. The itself camera cannot. Yes, because the itself camera, it cannot form the three-dimensional structure, of course. And for that you need a software to prepare 3D image. Now is it clear that why I need pinholes, and what is the detector, and how I can get the 3D data, the 3D image? So that is the importance of pinholes, to make the more contrast, high contrast. Otherwise, I will get less contrast in my image. So here again we'll discuss that how we can make a very high contrast image. So phase contrast microscopy, it is an optical contrast technique for making unstained transparent object visible under the optical microscope. So what is the difference between the phase contrast and ordinary optical image? So there are two optical element that involve. So one is the phase plot, another is the annular aperture. So one is the phase plot and another is annual aperture. Okay. Now these are the two added component on a ordinary microscope. So you put phase plate and annulus aperture. So that is the added on a simple microscope for a to develop a phase contrast microscope. Now of course, why I need why I need a phase contrast microscope. For example, if you are visualizing or if you want to visualize a EPDM polypropylene composite. Now, since it is transparent, so it is difficult to create a high contrast image. Okay, because both are almost transparent. The blend EPDM and PP is almost apparently transparent. So through this I can create, this is the negative phase shift and this is positive phase shift. So an annulus aperture is placed in the front of a focal plane of the condenser and limits the angle of the penetrating light wave. A phase plate is placed in the back of the focal plane of the objective, and the light waves which are not interacting with the specimen are focused as a bright ring in the back focal plane of the objective. So this is the phase plate and this is annular aperture through which you can create the contrast of your image. So if you compare the negative phase shift and positive phase shift, from here I can more accurately measure if there are the circular particle, a circle, the dimension in circular type, I can measure the diameter of this particle. But from here it will be difficult to exactly measure, and also the uh, if there are too much agglomeration, I cannot clearly visible, it cannot be clearly visible through positive phase shift data. And phase plate changes the phase by lambda by 4, and scatter light is phase shifted by lambda by 4. The phase shift is scatter light is caused by the difference in the optical path length of the specimen. So if the specimen has different component, so the path length will be different, and phase contrast is different. It is generated through the interference principle. So in that way, phase contrast microscopy differ from your conventional microscope. Now, what are the different components in a general microscope? So obviously there is eyepiece lens. So this is the eyepiece. There is a tube connects that eyepiece to the objective lens. So here is the objective lens, and actually there are 3 or 4 different objective lens uh, attached with any microscope, advanced microscope, and the cost is higher little bit, and they almost always consist of different power of magnification. Up to 100 times magnification can be possible. And rack stop, this is an adjustment that determines how close the objective lens can get to the slide. So you should put your sample here. This is the sample holder. You put your sample here. Just by using this bottom, you can change the distance between the lens and your objects. Just by rotating this, you can change the distance between the lens and your object. And the condenser lens is also another important component, and the purpose of this, focus the light onto the specimen. So actually light is coming from the back side, and through the conduction lens it is focused on your sample, and then the reflected light is coming to your objective lens. After that it goes through this connector to eyepiece, and then you put here a camera to get the image. So if we compare the simple versus compound microscope, so one is of course the compound microscope has higher magnification, and also there are number of magnifying lenses is uh, higher compared to simple microscope. And if I compare in terms of condenser lens, so condenser lens is absent in case of simple microscope, but in compound microscope we need condenser lens. The mirror that is used in simple microscope is concave reflecting, and in case of compound microscope, one side is plane and other side is concave. The source of light that used in simple microscope is the visual simple natural light, visible light, but for compound microscope you need a illuminator to make the resolution higher. The level of magnification that can be possible through simple microscope uh, only one time, but in compound of course we can go even up to 100 times also. And what kind of structure is visualized? In case of simple, it is a small hollow cylindrical attached to the base and is used to hold the microscope. And the structure of compound microscope, that is arm is carved and is used to hold the microscope. Now what are the application area? It can only used simple ways such as enlarging the smaller letter or to read a small letter. Just it has not in that much importance in your research, but in case of compound microscope, it has very vast application in biomedical field, and also to visualize the living organism, different bacterial or virus species. The compound microscope is very much used. And also through compound microscope we can check the grain boundaries, phase boundaries and microstructure. But below that, to visualize the crystal structure or to go up to nanometer level or fraction of nanometer level, it is not possible through the optical microscope, because the limit of the resolution is half the dimension. If the dimension of your objects is lower or smaller than the half wavelength of the radiation, I cannot resolve that part. So next come to electron microscope. Before that, first we will try to understand what is scanning probe microscopy. So there is two special term. One is the scanning and then probe. So it is a branch of microscopy that forms image of surface using a physical probe that scan the specimen, and there are several different type of scanning probe microscope or SPM. So first we will discuss AFM, that is atomic force microscope, and then we will discuss STM, that is tunneling microscope. Before that, just assume, for example, if a blind person is passing through a road, so he or she has no visual power. So how he or she can pass? So it has been seen that usually they use a stick. Through stick, he or she is sensing whether there are potholes or whether there are different harm or something like that. Through their stick, he or she is getting the signal. Signal means that's just through his or her brain. Uh, he or she cannot visualize, but just getting the sound through the stick, they can pass the road. The similar way, we can do the same thing in atomic level. So that is the probing. That stick, when it is the stick is touching the ground, that is called the probing. Similarly, here there is a very sharp metal tip is used, and it is probing your sample surface, getting the signal from the sample surface. After getting that signal, it has some uh, mechanical or uh, electrical uh, response, and through that response we will create the image. So let's first come the scanning tunneling microscope. So what actually happens? And there are two different mode. One is the constant current mode and another is constant height mode. What does that mean? Constant height means always the height from the probe to the surface will remain same. And what is the constant current? The current that is generating in between the surface and your probe, that is maintaining. That in that way it will probe the surface. So for that, of course, we need to provide a bias, and then the current will tunnel. from your sample surface to the probe. And the surface of the tip of this probe is very sharp. It may be in uh, one or two atoms actually interact with your surface. So this is the it is more clearly visible here. So usually one, two, or two, three atoms are actually interacting with the surface of your material. So you put voltage difference, and the tunneling is actually a quantum phenomena. So even it is not exactly touching the surface, through the tunneling process, the electron can hop. Basically, it is the hopping, and then your very small amount of current is generating, and after taking that current, the image is forming. So yes, piezoelectric tube means if there is a change in pressure, it will generate electricity. Now, how that pressure is changing? So, just 1 minute. So, obviously, we know that F equal to Kx, right? Sorry, F equal to Kx. Okay. So, how the force is generating? So, of course, the K is constant, and X is the deflection length. So, when that probe here, when the, for example, if your surface it is not absolutely smooth, and there are different components on your surface, and based on the interaction, the amount of uh, uh, current will be different. How? For example, when it is coming here, the same probe is coming here, so it will, the X is now low. If I compare this portion and that portion, the X will be low in case when it is coming here, right? So obviously the F will be different, force will be different. Now how I can measure that how much force is generating? That is because of the generation of the current. Now, piezoelectric material that use very small uh, pressure or current, or vice versa. I mean, you just put a very small pressure or force, it will generate a very small amount of current. That's why you need piezoelectric material. Otherwise, I cannot get that signal, because that is picometer level. I mean, that 10 to the power minus 10 or minus 11 order current, if it is generating, that much small amount of current to detect is very difficult. So that's why we need piezoelectric type. Huh. Okay, so that is the what is the basic theory to form an image? It is forming a matrix, array of matrix. For example, 1 minute. Let's say this is your uh, scanning area. Okay. Now, of course, the composition of the surface is different, and the height, it is not the same height from the probe and surface. Based on that, it is creating different amount of current. For example, here it is 1, 2, 3, 4, like that way. Okay. So each and every point it is generating an amount of current. So if I put in a, for example, let's say where it is generating current, it is 1, where it is not generating current, it is 0, or where it is generating current more than a few ampere, it is, I am designating as a 2. Let's say just go up to 10. So in that way, it is forming 1, 2, 3, 4. So it is forming basically a matrix, right? 1 minute. So in that way, if it is a matrix in my order in matrix, after interacting each and every point, then you use that array or matrix through a software to form the image. So if it is, for example, it is a just a white and black image, that means from where you are getting the signal, you put or designate as a 1, and from where it is not getting any signal, you designate as a 0. So 1 0 1 0 1 0 in that way. And after forming that matrix through software, you generate an image. So that's why actually image is processed. Is it clear now that how image is forming? So because your instrument is not actually, detector is not forming the image. From detector you are getting the signal. It is detecting the signal. After that, whatever the signal it is detecting, you prepare an array of matrix, and then the software will form the image based on the matrix. So what is constant current mode? So when an atomic step is encountered or when the surface is buckled due to the reconstruction, the height of the scanner will also have to change because of the overall topography. Now the image formed, so obviously if it is a constant current, so that tip, so it is not only scanning through the x or y axis, based on the height difference, it is also deflecting in the z axis also. And the image formed of the z scanner voltage that were needed to keep the tunneling current constant. So what is the benefit of constant current actually? For example, so since the tip is very much costly, sometimes it may touch your sample. But for that, if I use the constant current mode, so obviously when there are different roughness, so based on the height of your surface, it will deflect in the z direction also. So the chance of getting affected the probe will be less in case of constant current mode. But in constant height mode, the jet scanner voltage is kept constant as the scanner wings back and forth across the surface and the turning current. Exponentially dependent on the distance, and that is mapped. This mode of operation is faster, but on rough surface where there may be large adsorbed molecule present, so that the tip will be in danger of crashing. So that's why it is preferred to do the test under the constant current mode. So that your tip will not be affected, because whenever the surface height is changing, since I am already fixed the a specific voltage to keep the constant current is constant, so it will maintain that how much closer it should come. Whenever that current is generating, so it cannot come closer above that height. The next is the atomic force microscope. So in case of STM, what we are actually measuring, we are uh, the current that is generating, that we are actually detecting through the piezoelectric tube. Now in case of AFM, what is the force it is generated, we are measuring that. So atomic force microscope is the subcategory of the SPM, scanning probe microscope. So obviously here is also you are scanning as well as you are probing. Now SPMs are instrument that use a raster scanning tip to measure the surface properties such as local height, friction, electronic and magnetic properties, and construct a map of this data to form an image. So here is also you need a piezoelectric type material, and this is the cantilever. This is your cantilever, and this is your tip. And you actually how it is probing, it is not constantly going through this way, just it is uh, cantilever means whenever, since in case of AFM we are measuring the force, so based on that, that cantilever will bend. This is the cantilever. This uh, cantilever means nothing but what is the cantilever? Cantilever is, it is a, it is, of course it is a metal body, and here this is the tip. So we have already read during our uh, 10 or 11 that lever, how the force is changed. So that is the same thing is here actually we are using. So based on the force, it will bend. That's why we are using that cantilever. So here it is more clearly you can understand. So this is the probe tip, this is the cantilever, and whenever, since it is tapping the surface of your sample, now based on the force that is generating, depending on the interaction with the probe and the surface, it will uh, bend. This cantilever will bend, and when it is bending, now there is a laser diode. So depending on bending, you will get the uh, reflecting radiation at a different angle. Here is the photo detector, and after that you will get the signal, and then through the piezoelectric scanner, here is the computer to prepare the image. So there are, these are the important components part of your AFM. So first one is the probe tip, and for that, of course, it must be too much hard. So silicon nitride or silicon carbide, sometimes silicon itself is also used. So this part, this small part, triangular type shape, this small part is made of silicon nitride or silicon carbide. There is cantilever, there is laser source. So why laser source I need? Because depending on the deflection or bending, the whatever the radiation is coming through the laser diode, after this mirror, I am getting through the photo detector. 1 minute. Piezoelectric scanner, same here. Why I am using the piezoelectric scanner? Because the mechanism is based on the generation of current and force. Positive position sensitive photodiode, feedback control loop, and computer. Now how do electron microscope work? So first of all, you first form a stream of electron through the electron gun or electron source, either by thermionic emission, and accelerated them towards the specimen using a positive electrical potential. So here we are discussing the ACM, basically scanning electron microscope. Use aperture and magnetic lenses to focus the stream of electrons into a thin focused monochromatic beam. Focus the beam onto the sample using another magnetic lens. So why I am using magnetic lens? Because until and unless I am using magnetic lens, I cannot focus the electron beam. So that's why I need here magnetic lens. It is not normal like concave or convex type of lens. I need a magnetic lens to focus the electron beam. So to make it a much more pinpoint. And then interaction occur inside the irradiated area of the sample, and you collect the result after interacting that electron beam with your sample, and then transform it in an image. So the techniques used in polymer morphology is we have already discussed wide angle, small angle X-ray scattering, and then now you check the resolution. So in case of wax, 0.01 to 1.5 nanometer. In case of small angle X-ray scattering, up to 100 nanometer the resolution is possible. In case of TEM, you can go up to fraction of nanometer or angstrom level. Through scanning electron microscope, from 4 millimeter to 4 nanometer is possible, and optical microscope you see below 200 nanometer I cannot resolve because of the limitation of the wavelength of your visible light. So this is the different polymer morphology. So grains that actually 10 to the power minus 3 meter, powder particle dimension is 10 to the power minus 4, then spherulite type of polymers or two-phase structure if blend is there, lamella crystalline structure, molecular structure. So different uh, physical morphology and what is the resolution scale, and this is showing what are the different microscopy technique will be applied for or to visualize different structure of your material. Now, what is the principle of microscopy? So here this is your sample, right? This is the source of electron beam. So first of all, if the electron beam is passed through your material, this is transmitted mode. If it is reflecting back, that is reflected mode. In case of light microscope, the light is reflected. In case of electron microscope, electron is reflected. Same if it is in case of transmission, if it is the light microscope, so same light is transmitted. In case of electron, that is transmitted electron microscope, that's why it is same. Now, what is the interaction volume? So this is showing the region penetrated by the electron. So if this is your sample surface, your incident electron beam is coming, and it is not only the surface, it can go to few nanometer depth. Now when it is penetrating, so of course, but it is not, if it is not transmitted through, if I am only interested the scattered electron beam radiation, so of course from different depth the scattered electron beam will come. So here it is more clearly visible that what are the different electrons generate after interacting with the material. So first of all, this is the primary electron beam, and of course through the magnetic lenses. So this is the electron gun, electron beam is coming, this is the anode to make it converge. After that you use magnetic lens, converge it again, and your sample is, your specimen is here. Now there are different possibility of interacting your incident electron beam and your material, and after that there are different electrons actually generated. For example, agar electron is generated, secondary electron is generated, backscattered electron is generated, X-ray generated, what we have discussed during XPS also, cathode luminescence generated, fluorescent X-ray, diffracted electron, scattered electron, and transmitted electron. Now, which electron you are detecting, that is very much important. If you are detecting the transmitted electron, then it is called the transmitted TEM, transmitted electron microscope. If you are detecting the backscattered electron, so it is possible through SEM, sometimes agar electron microscopy, where agar electron is detected, that is called agar electron microscopy. So yes. Hmm. Yes, yes, these different actually uh, uh, all these electron and your X-ray generate when the electron beam is interacting with your sample. Yes, yes, your sample is actually transmitting these all type of electron, backscatter electron, agar electron, secondary electron, X-ray. So it depends on your sample only. Exactly, your detector will be different for different to detect different electron, and based on that you have different electron microscope. That which electron or which characteristic radiation you are detecting, based on that you are naming whether it is scanning electron microscope, whether it is transmitted electron microscope. In that way it is named with which electron you are detecting, but all possibilities are there. Now if you ask that whether it is uh, uh, in every type of material the X-ray will generate, that is the questionable, because to generate X-ray you need hard, what I have already discussed, I think ninth or 10th class, to generate X-ray, that electron, after that incident electron beam, when it is interacting with your material, it must knock out core level electron, and for that, if there is a presence of heavy atom, then only the chance of getting the X-ray will be higher. But the backscattered secondary electron and transmitted electron or diffracted electron are possible almost for every sample. And the agar electron, we will discuss that how agar electron or secondary electron generate, then it will be clear. Then it will be much more clear that from where actually what is called the agar electron, and whether it is possible for each and every element, or you need what is the criteria to release the agar electron or X-ray. So mainly the molecular weight is the main criteria whether that element will release agar electron or X-ray. Usually small at the lighter atom or lighter element will not uh, transmit agar electron or X-ray. Usually heavy element, those can release the agar electron, or that can also radiate X-ray. Yes. Ah, yeah, penetration. Yes, yeah, that's I am not saying about transmitted electron. I am saying about agar electron and X-ray. For example, that's why it is difficult to get very clear image of any polymer type of material through TEM. Not sorry, through FSM. Through TEM, it is transmitted through your sample, right? So that transmitted electron I am detecting. But if I am detecting through taking the agar electron, or if someone is investigating through the X-ray, fluorescent X-ray or cathodoluminescence, for polymer type of material, it is difficult, because since the polymer means only carbon and hydrogen mainly, it is very less chance to get very heavy element from your polymer. So usually those who are working on the metallurgy, they will actually investigate, or they study about agar electron spectroscopy and cathode luminescence or cathode X-ray. But in case of TEM, it is not the agar electron or X-ray. The same electron what I am uh, focusing on the sample, it is transmitted through the sample, and that's why you need a special preparation for the TEM analysis. You need a special preparation. You need TEM grid. Any doubt? Okay. So how backscatter electron actually generate? So it originate further from the incident beam. So whatever the primary electron beam is coming, the same electron is reflecting back. That is called the backscatter electron. It is not the electron from your sample. The same incident electron beam, when it is reflecting back, and if I am detecting that electron, that is called the backscattered electron. Okay. And what is secondary electron? Secondary electron escape from a region slightly larger than the incident beam. So it is coming from your sample. It is coming from your secondary. This is the coming from your sample. Agar electron is also coming from the sample. We will discuss what is agar electron. Now, how backscatter electron form? So when an incident electron collide with an atom in a specimen, and it is nearly normal to the path of the incident beam, it is scattered backward or reflected back. Where it is used? So imaging and diffraction analysis in the same. Production varies with the atomic number. So based on the atomic number, the how much it will scattered, that is also depend on the atomic number, that how much backscatter electron will generate. Higher the Z element appear, brighter than the lower Z element. That means whenever the element is heavy, so there will be the chance much more to scattered maximum a large number of electron that is coming. In that way, it is creating higher electron flux and you will get a very brighter image. Now, what is the secondary electron? This is the same almost what we have discussed during the XPS. So, formation, it is caused when an incident electron knocks an inner shell electron, for example, let's say K cell, and this causes slight energy loss and it will change the path of the electron, incident electron, and it will ionize, of course, since the K cell electron is now knocked out. So, of course, your element is now a positive charge. Now, that ionized electron leaves the atom with a small kinetic energy, and then that much energy it will use to release another electron. That is the secondary. Now, what is the purpose? To detect the secondary electron, to prepare or create an image, and it is related to the topography due to the difference in energy. uh, Based on the difference in energy, it will of course create a different array to form the image, and only secondary electron near the surface can exit the sample. So usually if you detect the secondary electron, you will get maximum data from the surface only. So if you see, so whenever the primary electron beam is coming, so it is the secondary electron maximum generate just below the surface or from the almost from the surface. So that's why you will get maximum data, or you can get much more clear idea about your surface when you are detecting or you are capturing the secondary electron. Okay. Now what is the agar electron? Agar electron is, it is the de-energization of the atom after secondary electron is produced. So after the secondary electron is released, then whatever the vacancy is created, to fill that, an electron from the higher energy level, it will come back, and then if again there is another chance, when that higher energy electron is coming to the lower energy orbital, that excess energy, it can release another electron from the same element, that is the agar electron. So during secondary electron production, an inertial electron is emitted from the atom, leaving a vacancy. Higher energy electron from the same atom can fall into the lower energy hole, that will create an energy surplus. How the energy is surplus? Because that electron is coming from the higher energy level, right? Say for example, it is coming from the 10 kilovolt to 5 kilovolt, just let's assume. So of course 5 electron volt energy is now surplus. Now to compensate that, it can release another electron with that much of energy, and that is the agar electron. So what is the use of this agar electron? It is characteristic energy that are unique for each element. So it is, since that electron is coming from your element, so obviously it is unique for each element from which they are emitted, and collect and sort agar electron according to the energy to determine the. So of course if you have different composition, 4 to 5 different element, you can you can assure that what are the different element present based on that energy of that agar electron. And AE has a very low energy and are emitted from the near surface limit. It is also, it is not very much higher depth. It is also from the near surface region. The next is the X-ray. So it is almost same. Yes. Name is, just ask. Huh. Yes. Yes. Exactly. Absolutely, you are right. So that's why I am saying it is the same that X-ray. Whenever that surplus electron, surplus energy, so there are many possibility. First of all, whatever I have discussed, that agar electron. Next, what you say, that it can also generate fluorescence. So if that excess energy is released as a X-ray, it is X-ray fluorescence. If it is release another electron, that is agar electron. That is the difference. So how that energy is compensated, that actually depends on element to element, whether it will generate X-ray, whether it will generate fluorescence type of radiation or agar electron. It depends on element to element. So that's why you are getting different uh, X-ray fluorescent, cathode luminescence. So these are all from your sample, that how much that surplus energy, how it is compensating. Is it clear now? Clear na? That same surplus energy, it can uh, release as a fluorescent X-ray or cathode luminescence or agar electron or continuum X-ray. So that is the surplus energy, then that different possible way to compensate. This is the same. That's why if the surplus energy is compensated through the X-ray, it is called energy EDS, energy dispersive X-ray spectroscopy, and we know that through the EDAX we actually check through from FESM. There is also, with FESM there is also another component to that is EDAX, so that we can characterize what are the different composition of a sample, because since it is the inherent property of your element, so of course there will be the variation. So in that way we can check how much homogeneous your blend, or uh, what are the different phase present in your material also we can check. The next is the transmitted electron microscopy. So that means whatever incident electron beam is coming, it is penetrate through the sample, and uh, I think it is not given here. So next week we will give an image of TEM. Anyway, so it is the transmitted electron. So we are detecting the electron, those are passing through the sample. So it is penetrating through the sample. After the penetration, the transmitted electron, we are capturing those electrons. So of course, we can use to determine the thickness, crystallographic orientation, atomic arrangement, phase present, etc. Now ACM actually yields these following information: surface feature, topography, morphology, size, uh, shape, and agreement of particles. We have also checked the compositional analysis through the EDAX. And for that, of course, the one limitation is your material should be conducting. If it is not conducting, we should coat with a conducting element. Otherwise, electron beam cannot interact. If it is electrically insulating, that electron beam cannot interact with your material. So for that, usually we used to do gold sputtering. So that image is given here. So you put your sample on a carbon cloth or carbon paint. After that, you coated your sample with through sputtering to make it electrically conductive, and then you put your sample inside the instrument. Now this is the components of transmission electron microscope. So of course there is a source to generate electron beam. There is also condenser lens, specimen stage objective lens, imaging system, and CCD camera, that is charge couple. Uh, I forgot the D, charge coupled diffraction or something else. So through TEM, we can generate bright and dark field imaging, and through this we can visualize the internal or ultrastructure even in the fraction of nanometer scale, to investigate or to identify whether there is a form of a defect. We can check that also, because of course if there is a defect, so there is a the scattering will be different. And through HRTM, that is high resolution transmitter electron microscope, you can check the interfacial structure. If you are uh, preparing a for polymer people, if it is a blend of two polymer, you can check the interface, and of course interface plays a very significant role to determine the mechanical property of any composite. To identify the defect structure and why it is high resolution, we will discuss that how HRTM image differ from the simple TEM. And electron diffracts, through electron diffraction we can get idea the crystallographic information of your sample. And electrical energy loss spectroscopy, that is also can be accommodated with TEM, and you can analyze chemical composition or other uh, bio even in biomedical field you can accommodate EELS, and of course EDAX also you can accommodate with your TM machine. So this is the difference between normal TEM and high resolution transmission electron microscope. So if it is uh, a blend of CO2 and silicon, you see here you can clearly visualize the interlayer of this two composition, but here it is much more blurred. And why? What is the difference? Here the incident electron beam is much more precise compared with your normal TEM. So that's why you are getting that much of bright image. So TEM actually is a multi-purpose machine. So of course you are getting the idea about your uh, bulk structure, bulk morphology, your defects, microstructure. Vice versa, you also can get idea in the atomic level. So whenever you are getting that lattice parameter or orientation from the HERTM, you can go up to 0.2 nanometer resolution. So microstructure defects as well as atomic structure you can analyze through the TEM, and those are actually uh, because of the elastic scattering with the electron incident electron beam and your sample. Side by side, through the EDAX you can get chemical composition, and also the if you check the in situ effect of heating and cooling, that can also be studied through the TEM instrument. So that's why it has a multi-purpose role from microstructure to atomic structure as well as chemical composition you can determine through the TEM analysis. Now what is the problem? The problem is the sample preparation is very much important. So the usual preparation technique applied to inorganic sample, particularly for TEM investigation, cannot be applied, and the preparation of ultra thin specimen from bulk polymer is often difficult. So since it is transmitted electron we are capturing, so the thickness of your sample must be very low. If it is not so, less number of transmitted electron will you will get, and of course that will create problem as the image formation. So first of all, the limitation is you must have a very thin sample. And in case of polymers, since they are organic substances, so they are particularly sensitive to electron beam irradiation. And the contrast between structural disease is often very low, as the polymers are organic molecules and consist of usually carbon, hydrogen and oxygen, and that interact very weakly with the electron beam. So thank you. Yes. Actually, see that from FSM you can also get the data, get the surface morphology and structure, etc. But for TEM, uh, sometimes you may get the what you want, but since these are very lighter element, so the interaction with electron beam is little bit weak. And since we are getting the we are taking the transmitted electron, we are in case of TM we are capturing the transmitted electron, right? So obviously, if it is the heavier element is interacting, the path length of the transmitted electron will be different. So in that way, the scattered or transmitted electron beam intensity will vary depending on the composition of your material. So if it is only carbon, hydrogen, oxygen, so in that sense, it is little bit. Uh, and if you compare with other inorganic type of element and your organic, so the tame image maybe will be much more brighter for heavier type of elemental composition. So that is the concern. That does not mean that your polymer sample cannot respond or you cannot take images through TM. Of course, you must go for the TM, but if you check uh, the contrast or the brightness, so the heavier element sample will give you much more brighter image. Yes, something else. Yes. See, actually, why we should go for TMR? First of all, we just want to know what is the uh, sample, I mean, the size or shape of your molecules, right? Now, whenever if somebody is working on a small molecule synthesis, so he or she, it is not that much important for her research or for his research, the TM data. It may not be. I'm not saying that it must not be important, but it depends uh, the research field also. For example, if someone is working on metallurgy, for them it is very much important to go for the TEM, to just object what is the defects, what is the if someone is doping is working on doping, so of course through TEM he can visualize whether the crystal plane or lattice disorientation is happening or not. You can visualize through HRTM image. That much of resolution is possible. But if someone is working on organic molecule, it may not be that much significant. It is possible just to, if you want to see the morphology, surface morphology, I can get data from FSM. Because why I should go for TEM? To get the data in 2-3 nanometer level scale, that is difficult to get the clear image from FSM. That's why I should go for the TEM, to know the what is the crystal lattice orientation or dislocation or other defects are happening or not. Is it clear? Or if you have any doubts, you may ask me, because I have time till now. But I think last week you have asked regarding grading. So give me just another week. Uh, I will discuss, even if it is possible, we can take another extra session, because this is the 10th week. So we have another 2 weeks, and if it is possible or if it is okay for you, we can take another session also, because I have left. I remind that XRF I have not fully discussed, so maybe I have to take another session. In that class, we can discuss about grading. So I just want to request you, if you can send me a mail what exactly your question is, so it will be much easier for me.